بسم الله الرحمن الرحيم. المتحدثون الأعزاء، المشاركون والضيوف الكرام، السلام عليكم ورحمة الله وبركاته، وطاب صباحكم. معكم سالم رجب، المدير التنفيذي لسبائك للتعليم والتدريب بمملكة البحرين، عضو في مجلس إدارة جامعة التعلم الافتراضي قسم السياسات البيئية والطاقة وتنمية المجتمع. يطيب لي وباسم البروفيسور أحمد الناوي المؤسس والمدير التنفيذي وأعضاء مجلس إدارة جامعة التعلم الافتراضي الترحيب بكم في اليوم الثالث من مؤتمر جامعة التعلم الافتراضي، وذلك ضمن فعاليات المعرض الدولي للطاقة الشمسية والنجاعة الطاقية الذي يقام في الفترة من 7 إلى 9 يونيو 2022 تحت الرعاية السامية لصاحب الجلالة الملك محمد السادس ملك المملكة المغربية. Dear speakers, distinguished participants and guests, good morning. This is Salim Rajab, the Executive Director of SABAIC for Education and Training in Kingdom of Bahrain, member of the Board of Director of the Virtual Learning University, Department of Environmental Policies, Energy and Community Development. On behalf of Prof. Ahmed Al-Nawi, the Founder, Executive Director, and members of the Board of Director of the Virtual Learning University, it is my pleasure to welcome you on the third day of the Virtual Learning University Conference, which held as a part of the activities of the International Exhibition of Solar Energy and Energy Efficiency from 7th to 9th of June 2022, under the high patronage of His Majesty King Mohammed the Sixth, King of Kingdom of Morocco. Prof. Ahmed, the floor's yours, please.
You're still muted.
Prof. Ahmed,
yes,
you are.
Yes.
It's okay.
Sure. Thank you very much. I will give some detail about our speaker, and he will talk about green hydrogen and solar fuel with artificial photosynthesis. And Professor Dr. Hannappel is very well known, working hard and with a very good result, excellent result in this topic of green hydrogen, miming the nature. So Professor Thomas Hannappel, I know him since many years while we are working together in the same center, Helmut Center, Berlin. Now although he's connected to Helmut Center very much, working together, he is full professor at Illinois University of Technology, Institute of Physics. His research focuses on efficient solar energy conversion, high performance optoelectronic material, and critical interface. So it's a fundamental work and application. Before, he was scientific director at CIS Research Institute, Erfurt, acting director of the Institute Dynamic of Interface Reaction at Helmut Center, Berlin, department head at the Hannappel Institute before Berlin, and lecturer at the Free University since 2005. In 2003-2004, he conducted research on silicon 3,5 heterojunction at National Renewable Energy Laboratory. It's a very promising topic. He received his PhD at the Technical University Berlin with study on photo-induced charge dynamic. He performed in the Department of Physical Chemistry at Friedrich Institute. I want to thank him very much because he's always available to help Morocco and to bring us new science on fundamental problems and application of green hydrogen, miming the nature and using semiconductor like 3,5 compound. Professor Hannappel, thank you very much, and the floor is yours.
Yeah, thank you also for the very kind introduction. And indeed, it's always a great pleasure for me to be invited and to contribute to the very good activities I I see all the time occurring in Morocco, and this is really very important and very good to see. And I understand that I will speak about 50 minutes. Is this in the appropriate range? You can stop me and tell me if there's only 5 minutes left or so.
It's fine.
Yeah, so thank you very much. Yeah, indeed, I will talk about artificial photosynthesis mimicking nature. This would be fantastic, doing the same thing as plants are doing, and the same thing, and I would like to show this, we can do in parts, of course. The first step is the production of hydrogen, which occurs by splitting water with the help of sunlight. And this would be fantastic to mimic, and I will show that we could even do more than this. And just to say, here we had already shown in the past, I will also show this, that we get really very promising efficiencies. The solar to hydrogen efficiency record, which we gained together with some other groups, which I also introduce, is so far at 19%, which is really very good and promising. We always see that we have a lot of challenges which are which have been addressed by Professor Smalley, Nobel Prize laureate in 2003, and he was putting energy at the first place. We need to say that this is, of course, renewable, sustainable energy. And if you look at the list, we would see that even further challenges like clean water and food and the environment also are dependent on energy. And even the other points which we can see here, like poverty and wars, diseases, they might also be addressed by the availability of enough renewable energy. So the point I would also like to address today is that it is just more than only having a semiconductor, which we need to convert solar radiation into free energy to convert this in a successive process into solar fuels. And what we need is multi-junction solar cells. So we need a stack of solar cells, which is challenging and complex. And this I also would like to address today. And we need a lot of different ingredients. So it is highly interdisciplinary and addresses many different directions, not only chemistry, but also physics, physical chemistry, nanotechnology, electrical engineering, and many things more. Today, I would like to, in particular, show you what are the limits for the efficiency of water splitting. I would also like to address the challenges of the beneficial semiconductors. Also, of course, what we also need always to see is costs and the major point of interfaces. Interfaces is something which we are addressing in our team in particular. And here you can see our team, but we are always connected with important and very good partners. I would like to show this also in the following course of my talk. Here you can see where we are right now in Germany. Of course, we are in, I am right now in Ilmenau, having a professorship in the group Fundamentals of Energy Materials since 2011. And Ilmenau is basically in the middle of Germany. Normally, you wouldn't know this since it's a smaller city, smaller town, but it has a great environment, not only with regard to nature, but also with regard to history. As you can see here, we have built up really blooming landscapes in in the scientific environment here in Ilmenau. And this you can see at many different infrastructure buildings here with a lot of clean room and so on. So now I would like to switch to the topic where we are. We have the challenge of climate change. You can see this if you look at this history of temperature development on the planet. You can see that we over the years get much warmer. It's of course small changes in the range of so far sub Kelvin or degrees Celsius, but still it's a major influence on this planet, which we are having in the course of these changes. And this is, as you would know, I think so, is due to the greenhouse effect. We have a greenhouse warming due to the increase of the amount of carbon dioxide, and in parallel also the increase of water vapor as well as methane and other greenhouse gases. We have this major changes which we can see. The source of this is of course the sun, the power source we have on in really impressive dimension, as you can see here. However, we can of course just use the resources which the sun has produced in the past and which we have in the nature, and to more or less dismantle our planet, what we are doing right now. But we could also use it to provide all the energy which we need. The global consumption, just as a figure, is in a range of 20 terawatts, which we right now use at this planet, on this planet in average. And as you can see, the amount of energy which we can get from the sun, also of course using wind energy and hydro, is much more than that what we basically need. Just to say it again, we are basically not talking about energy, we are talking about power. So energy flow, and this is very important if we finally look at the microscopic points which I will address here when we are converting solar radiation into free energy. Just to show it here, we have different ranges of energies which we can use, and what we basically need is energy in the range of 20 terawatt, as you can see here. And this is something which we are basically approaching. If you are looking at this curve, at these curves, where you can see the development of the global capacity of energy given by solar energy conversion, by wind energy conversion, nuclear and hydro. If you follow this curve, then you can basically see, and this is where we are right now, and this is very promising. We are currently at around 1 terawatt peak in the capacity of solar energy, which we are providing by solar cells. And if you follow this curve, then we can be very optimistic, since already in the year 2030, we could be really at very serious values, as you can see here. And what I already was saying, I am always impressed, and I think this is very good to know, that there is much activity and much work done in not only, of course, in Morocco, but in particular in Morocco. And I'm always glad to see this. Okay. So what else do we need to talk about? It's not only, of course, the provision of energy. What we also need is energy at the appropriate time and at the appropriate spot. So we need to talk about storage, mobility, system stabilization, and energy cycles. And this is a very nice cartoon. I always like it very much, since this is basically, of course, a fancy picture, but it shows what we can do. We can convert solar radiation, solar energy into solar fuels. That's what we are following recently. And basically, besides hydrogen, which is the primary, the first solar fuel, we can do in different ways also the conversion of hydrogen then in different other fuels. And we can also, and this is basically the next step, also what nature does, we can reduce carbon dioxide also in different solar fuels. I will get to this point. We have a very large initiative right now to basically collect forces to get a so-called collaborative research center to create this together with other groups. I will also briefly mention this. This is something we are planning for the far future. I will talk about this. For the reduction of carbon dioxide, which is even a larger challenge than only converting hydrogen, we need even more free energy. I will get to this point. This is due to different reasons. One of the reasons is that we are doing photoelectrochemistry, electrochemistry at interfaces, where we have a very difficult interface between the solid and the liquid, and where we need to consider also, besides the free energy, which we just need, also so-called overpotentials. I will briefly also get to this point. Just to show this here again, in energy, there is not so much difference between the production or the splitting of waters, the production of hydrogen. We can also, as I was saying already, produce other fuels such as methane or formic acid, and even more. So what we also need to address is a very complex and very important point, where we already had at least 2 Nobel Prizes looking at this for Gerhard Ertl on catalysis, and also recently last year on the Nobel Prize on catalysis. So catalysis is also an extremely important point. This is not only for the direct. What we need to say is that we need to, I will explain this on the next slide, just to say this already here. This is the direct way, the second way, as I am indicating here, to convert solar light into solar fuels. What plants are doing. The alternative is first production of electric power, electric energy, and in a second step, then driving electrolyzers. This is also called power to X. But there is a large overlap between these two routes. I will also explain this. Basically, what we in both cases need to do is, of course, the transfer of charges from a solid state into an electrolyte, into the reactant. I will talk about this. So here I just want to show again that we need to see that we have a large system where we need to combine different cycles. What you can see here, we can rely on the electricity cycle, then the hydrogen cycle, what I was already addressing before, done either directly with photoelectrochemistry or indirectly by the provision of electric power, and then in a second step driving an electrolyzer. And then finally we can reduce carbon dioxide and create different solar fuels. And this can all play together, and this is of course in every regard highly complex. So I'm continuing to talk about photoelectrochemical cells, just to show this here again. This is two different routes. Sunlight use for the conversion of energy, either directly leading, like in plants, to solar fuels, or indirectly by driving electrolyzers. Both have, as I told, large overlaps with regard to the utilization of semiconductors. In both cases, of course, it would be if we want to use solar cells to produce electric power, we in both cases need semiconductors, and also as another example, the catalysis. In both cases, we need to have very good catalysts, appropriate catalysts. Some advantages to do this directly, to use the artificial leaf, is that we have much lower current density, so we could afford to have, of course, other alternative catalysts. Catalysts are a big point, since normally you use very expensive materials like platinum, iridium, rhodium, ruthenium to build appropriate catalysts. And here the search of catalysts with a larger availability, as well as being, of course, cheaper, there it could help to have just much lower current densities. Secondly, thermodynamically, in principle, this way is much more favorable, since we do not provide the heat, since the heat we get from the environment. This is a significant amount of energy thermodynamically. Then changing dynamics is easier with such photoelectrochemical cells. We have not to balance two completely different systems, like the provision of electrical energy, and then in the successive step, the electrolyzers. And we have only one electric circuitry, and of course this is a very big point, it's decentral. We can scale it at will. So very small, very large, medium, any size, like solar cells, which also would be, of course, very good to have. Okay. just more or less summarizing here all the different arguments I already touched. So we are talking, of course, finally about costs, about availability, and scaling. Yes, so just recognizing again, we have basically two different ways with an overlap in the challenges, but with a different approach. The approach I am talking about is the direct conversion of solar energy. You can basically see this here in this, oops, maybe it's too loud. I reduce the noise, I'm sorry. Yeah, but what you can see here is basically what I mean. There's no wire to the outer environment. There's only solar light and the cell in the electrolyte, and just by illumination, without any driving force from the outer environment or by any connection to the outer environment, we would form bubbles, and for hydrogen and oxygen if we are splitting water. Okay. So, and here, as I already told, we made it in a very good cooperation with California Institute of Technology, with Caltech, where we have where the Joint Center of Artificial Photosynthesis has been established, now turned into LISA, the Liquid Solar Alliance, and together with the Helmholtz Center in Berlin, and in this large group, we made it to show that it is possible to do this really already with promising efficiencies. And in the next step, we are right now also in a project, in a network project, where we want to show that the direct and efficient CO2 reduction is also possible. And here we have shown that we basically need tandem cells. This is a very important point I would like to explain in the next slides, which is not very easy to follow, since it's of course physics, physical chemistry, semiconductor physics. I will briefly try to introduce. So here in this regard, there is the so-called detailed balance limit, also well known as Shockley-Queisser limit. I just briefly want to say this is a physical limit which we have. And there's always the question, could we be better than this? And I just want to briefly address this. What we basically do, if we see the sun spectrum and then we are absorbing light in a semiconductor, then we are immediately losing a lot of energy. This energy we cannot prevent to lose if we are just using one semiconductor like silicon. This is similar to a solar heat engine. Also, a heat engine cannot be better than the Carnot efficiency. And this is very similar, a good comparison, since we are basically doing something very similar here. And this leads, due to the energy loss of the thermalization of charge carriers in the semiconductor, and due to the band gap, which we basically need, but on the other hand, we are of course not absorbing light, which has a smaller energy than the band gap. And in this course and this principle, due to this concept, we are basically limiting the efficiency with a single junction solar cell at about 30% efficiency. And this is due to, I don't want to go too much into detail, but this is due to the constraints, to the nature which we have. The nature is that the sun has a certain temperature at around 6,000 Kelvin, and the Earth has a temperature of 3,000 Kelvin, which basically gives us already two temperature reservoirs which are limiting the energy. In addition, we have more constraints. Even if we would assume the very best, only having radiative recombination of charge carriers, no non-radiative recombination in the semiconductor. If we are assuming that we have only one semiconductor, and that we are basically completely absorbing the light which is shining on our solar cell, and so on. If we have all these constraints, we can see at one sun without concentration, we are limiting the efficiency at around 30%. I'm talking about now solar cell efficiencies. We can see that in the solar fuel production, in the hydrogen production, we are even more limited. I will explain this also. We can be better with different changes of these constraints, for example, by light concentration, then we get to a higher theoretical limit, and also we get much better practical values, as we can see. Okay, I will briefly now talk about semiconductors, since they are the important, this is the important body, the material which does the very essential step. It's a kind of miracle to have a piece of a solid state body which can absorb the light and in the material already convert this solar radiation into free energy and store it for a very limited short time. I will show this. This is magic, very good to see, and it's fantastic that we have these semiconductors. Here you can see the main thing in a semiconductor is that there is a band gap, and if we absorb light, we are creating a lot of charges in this semiconductor. This is the first step, basically the most important step. Absorbing the light, creating many charges, a high concentration of electrons and holes, and they are providing the free energy afterwards. This is shown here. I don't want to explain this in detail, but we can see this in the form of so-called Fermi levels. These Fermi levels, this is the chemical energy of these electrons and these holes. And this can be stored for a very short time, and we can use it then. We can use it, for example, and we can really see it if we, for example, are doing using them as light-emitting diodes. Light-emitting diodes are converting exactly this energy into light. They are they are basically illuminating. They are emitting. This is the generation which we have by absorbing the light. The recombination in the best case would be just by the emission of light, and alternatively, we can extract these charges. Extracting these charges mean we can use them, and we can use them either just for the production of electric current, power, or, and this is the point here, for the reduction of the oxidation. I start with the oxidation of water, and then with the reduction of the H+ ions, which we are producing when we are oxidizing water. This is the cycle which we have if we are doing water splitting. just briefly touching these points here to show that this is so important. And then we have a lot of processes which we do not want basically to have, which is so the so-called non-radiative recombination, also called impurity recombination, or also called Shockley-Reed-Hall recombination, many names for the same thing, or, and this is very similar, the recombination at interfaces, where we are just using these charge carriers which we would like to would like to extract from our semiconductor, and not to be recombined in such a way. Okay. There's much more to say. I just wanted to say this briefly, and this is very important. If we are regarding the semiconductor physics during the conversion of solar radiation into free energy. And then we can use these, and if we see that we only have one semiconductor, then we can just calculate, how much energy gap do we need, how much energy does the solar spectrum provide, and if we compare everything and look in detail about these energy values, which are given by this free energy, Fermi level splitting, as well as the so-called overpotentials, which we need to transfer charges over the solid liquid interface into the electrolyte, then we see that one semiconductor is not very good to be efficient. And we can basically make it much better and perfectly if we are using for water splitting two junction cell, a tandem, which you can basically see here. In this case, we can exploit the solar spectrum very well as transferring charges into the electrolyte and using the optimized amount of solar light for the conversion of or for the splitting water for the production of hydrogen. Okay, this was a very small detour through semiconductor physics. Finally, given by all the important values here, the so-called diffusion length, the lifetime of charge carriers, the mobility, this is all complex semiconductor physics, but very important. I wanted at least briefly address here. And then we can look how it works in such a tandem. We can see we are creating electrons and holes, and we have isoenergetic recombination in a so-called tunnel junction. And finally, we can extract the charges here into the electrolyte to produce hydrogen and oxygen. For this, we need very good catalysts, as you can see here. The high catalytic activity, this is a real challenge and a very complex scientific problem. Also, many groups are working on this too. Very important for many processes, also for batteries, not only for water splitting or solar fuel production. In many cases, we have these catalytic processes and the solid liquid interface. Also, the stability is always a problem, since this is a very dangerous interface, of course, which can corrode. We can have corrosion at these interfaces, and then it's just degrading. Okay, and if we do this appropriately, that you can see here again, in such a semiconductor stack, then we can be very efficient, as I already told, This is exactly what we did in our approach. Yeah, here you can see the whole procedure in the real structure. It's exactly like I was showing, like in a textbook. What we do is the production of enough free energy here for splitting water by all these processes, which I have explained before. And yeah, it's perfect, close to perfect to have this, but there is still a lot of very difficult challenges which need to be solved, which I already touched in my talk so far. And the realization, as you see, is not at the optimum what we did. The combination of the different band gaps is an important parameter besides the properties of these semiconductor layers is also a point. But as I told, many problems, questions, understanding what we need to contribute, and also the costs, of course, a very important parameter. This does not sound very scientific, but it's also extremely important. So I will touch this point briefly. Also, costs, how to deal with it, and in particular, I would like to refer to the successful system which we have used using the so-called 3-5 semiconductors, like gallium arsenide, indium phosphide, and so on. One point is the very expensive material. The material itself is basically an expensive part. Also, of course, the production, the protocol, how to prepare these materials, both can be tackled really significantly. And that's what we are also doing with partners, tackling these cost issues by the change of the preparation mode, the preparation protocol, as well as just simply the substrate. Normally, the substrate is very expensive since it's a very thick layer of, for example, gallium arsenide or germanium. And this is, of course, much thicker than we basically finally need the absorption layer, and it's very complicated. And that's what we are trying to do. We try to combine these 3-5 semiconductors with silicon. This is already a very old question, already Nobel laureate from the country where I'm here in Thuringia, Thüringen in Germany, Herbert Krömer, he was also tackling exactly this issue, growth and understanding of 3-5 on silicon preparation. What you can see here, there we would have many different opportunities to use exactly these silicon 3-5 combinations as very efficient layer stacks, ranging from different materials like the nitride, dilute nitride materials, as well as quantum well structures, as well as combining these material by changing the lattice constant, as well as using nano wires, nano rods for the solar radiation absorption. I don't want to go much in detail, just saying that we do considerable work at this point also with very good results recently. Also very promising to see that with the preparation of 3-5s on silicon, silicon as the working horse of the semiconductors, and 3-5s at a kind of upgrading this working horse. There we already showed recently very good values in collaboration with partners. or let's say the other way around. This is Markus Pfeiffer from Solaire, from Fraunhofer Institute of Solar Energy in Freiburg, and yeah, there we have also a very long cooperation already in the past, and the growth of III-Vs on silicon is a very important issue, just to say this. So finally, I just want to address also the difficulty. The difficulty here is exactly the interface, the interface between III-V and silicon. There is a long story to explain this in the microscopic detail. I don't want to do this here. I just want to show in principle what is the approach to solve such a difficult problem. To look at an interface which is buried and where we really need to look at the details of the atomic structure. And it's really necessary to solve this problem. And this we do in our group with a lot of different methods. So this is a well-known challenge. Also, Herbert Krömer was already saying the interface is the device. Also, another Nobel laureate, Wolfgang Pauli, was addressing this by saying the devil's work is the interface, when basically saying that the bulk, the volume is already a challenge, but this is, as I was already saying, something which we can get in a very good control, in a very good manner, but the difficult thing is the interface. And here we need to look with many different methods to understand the atomic structure, to look at the defects which we are creating, just recognizing them, and of course to look, and this is the important thing, during growth, in situ, during the preparation, already to see what is happening. Do we already create defects or not? How does it look like in the microscopic structure? And then after all these processes, we can look at the very different interfaces which we have here in the tunnel junction, as well as to the environment at the solid liquid interface, between the catalysts and the electrolyte, and between the catalyst and the absorber, and so on and so on. There's a lot of questions which we would like to address, as I already was saying, in a large initiative, as I am showing here. This is a so-called collaborative research center we would like to establish with all these partners at Technical University of Darmstadt, which would be our partner university, and also external partners like TU Berlin, Helmholtz Center Berlin, and Fritz Haber Institute, and more satellites. That's what we would like to do, and I think I'm almost at the end. I already showed that this multi-absorber approach is very important, a tandem approach, where we would like where there are, of course, more candidates for good tandems, like, for example, the combination of silicon and perovskites, where Helmholtz Center created very impressive results and new records. This is basically the perovskites, of course, very interesting semiconductors. Also with challenges, yeah, this is the sites which we can provide in Ilmenau and also in Darmstadt. What we would also like to establish here is, of course, the experimental environment using synchrotron radiation to look at the different parts, not only, but also at the different energetic ranges, at the different ingredients, like at the surface, the change of oxidation states, for example, at the valence band directly using valence band spectroscopy and core level spectroscopy to combine all this together with the appropriate environment to look at the solid liquid interface. This is all huge challenges which need to be addressed in a larger initiative and with many different partners. This is our environment, for example, in Ilmenau to look at the interfaces. You need, of course, the provision of the preparation of the growth chambers. In our case, it's metal organic chemical vapor deposition. This is these blue machines, which you can see here. And to combine this with surface and interface science, as you can see here, for example, with these different instruments, photoelectron spectroscopy, Fourier transform, infrared spectroscopy, and so on. This is just to show that we have a large variety of instruments. A very important point, as I was already saying, is the combination of optical in situ spectroscopy and the preparation itself, and then in combination I could also address all these points to look in an operando mode at the interfaces, and also to address, for example, the dynamics of the charge carriers. So I would like to summarize. Basically what we have seen is it is possible to grow appropriate material structures to mimic nature to produce solar fuels. The primary solar fuel is hydrogen, already with promising efficiencies, but it is complicated, and there is many questions to solve, which are in the simplest idea described by the parameter costs. Costs, of course, involve all the other parameters like stability, since if such a device is not stable, of course, it's not cost effective. And then, of course, all the materials involved, since if they are too expensive or not available in larger scales, they are, of course, also not cost effective. And all the other questions I was addressing, the interfaces to be efficient, to be stable, to understand everything. This is the most important point, and there is much space for more understanding, and this we would like to address to make finally, to provide, and this would be a dream, I think, of all of us, to have a scalable device which can produce just as nature is doing with artificial photosynthesis solar fuels. So thank you very much for your attention. Of course, I also would like to thank for financial funding and all the partners which we have. And of course, I'm open for any kind of questions.
Thank you very much, Professor Thomas Hannappel, for this very...
You are still muted, aren't you? No, my speaker is off. I'm very sorry for this. Okay. I didn't hear you.
So it's a very multidisciplinary...
I cannot hear you. I'm not sure why. Maybe it's my point. I see. I'm very sorry. My audio is off.
Okay. Do you hear me now?
Maybe I stop the presentation. Maybe.
Yeah.
Then it's getting better.
Maybe you have the
cannot hear you. I'm very sorry for this.
Just look in your computer if you can switch on the sun, and then maybe.
Unfortunately, somehow I have no audio currently.
Okay.
Maybe I quit the meeting and come back, and then
Okay.
I would hope it's getting better.
Okay.
1 second, please. I quit.
So after the KAE, the questions and answer, we are waiting Professor Hannappel to switch again on. Then we will move to afterward to Professor Mohammed Nazaruddin. He's one of the prominent researcher on perovskite. So I will talk about his biography. So let's wait just Thomas to come back and see if he can activate his audio.
Now my audio is back. I'm sorry.
Yeah? Okay. So we just try to, sorry for Nazaruddin. We will just make some questions and answer. So the Ustad Salim, can you just
Yes, as Prof Ahmed mentioned, now it's the Q&A for questions or comments or invent anything that you want to say about. You can write it in the chat or you can raise your hand also. Who wants? Okay, I think back to you, Prof Ahmed.
Yeah, okay. So I have one question about this technology, which is maybe in nature, when it will come to the not commercialization, but at least some prototype. And do you have an idea how you are planning this?
Yes, we are currently already working on this. There is a huge project funded by the Federal Ministry of Education and Research, BMBF. It's called H2 Demo, where we are with many partners for one specific type, already working on a demonstrator. Of course, the demonstration itself in a smaller cell, we have already shown. So there won't be, I think, one point of time where we have perfect prototype. But within the next 10 years, I would think 10 to 15 years. This would be my estimation. We will approach to from understanding to designs. There's many things to think about, architectures, how exactly to design, and finally, of course, about demonstrators and prototypes and the materials. But in this range, 5, 10, 15 years, having a first demonstrator in the next 5 years, I think it's possible to show this, but to optimize it, to improve it, and then to see how to solve the different problems. This will take 10 to 15 years, but I'm confident that this is timescales which we will realize.
Thank you very much. Thank you. So
there is Prof Nazaruddin, please. Welcome.
Yeah, very nice talk, Professor Thomas. So I really enjoyed your presentation. I come back to the question regarding the stability. You, in your last slides, you touched the stability issues, but I come back again to the same issue. When you are using this type of gallium arsenide, gallium indium arsenide, and gallium indium phosphide, so you are immersing in the water solution to oxidize water. How long you can these semiconductors can work in water environment?
Yeah, this is a very important point, and of course, maybe the hugest challenge. And indeed, there is different ways how to prevent corrosion. So far, the stability is not so long. There is stability ranges of 100 hours, 1,000 hours. but already in these time ranges, you see degradation. But it has already improved. What we are talking about is how to protect these interfaces from corrosion. There is ideas, of course, of protection layers, metal oxide, like titanium oxide. But here, of course, we need to understand how exactly to prepare the titanium dioxide so that there are no defects and starting to degrade exactly these protection layers, these functional layers, passivation layers. But it's a huge challenge. One needs to prepare. There is materials which are basically more or less stable, like titanium dioxide, which works very well also for a longer time, which unfortunately is not the appropriate semiconductor. But by the combination of these different layers, very good semiconductors, very good protection layers, and combining them, I think there's ways to solve this problem. But
okay, I don't know whether I have time to ask one more question. If it is, can
Go
I
ahead.
ask?
Go ahead.
You showed a very nice demonstration of water oxidation using this orange type of material. Is it a ferric oxide or ferrous oxide? If it is so, how do you extract charges? How long these materials are working?
You are talking about
The demonstration which you showed, the bubbling of the orange materials in a cell.
Yeah, this is, of course, as I already told, limited in time, and the stability is, as I told, a problem. And in our case, we have been driving these processes with two different variants of tandems. One was the later one with 90% efficiency with a titanium dioxide protection layer, and there we got efficiencies over a range of 100 hours. The other one was without protection layers, intentional protection layers, but with in situ passivation of the aluminum indium phosphide window layer. There, you can see this in this publication, this Nature Communication publication, where we did these phosphate passivations at the interface. But still, this is an issue which is not completely, not at all completely solved.
Okay, thank you. I appreciated your answer. Thank you.
Thank you. Back to you, Prof. Ahmed.
Okay, thank you very much, Professor Thomas Hannappel, for this very, very important talk, which is the future. And you are always welcome to Virtual Learning University to give your talk every time.